Hello, everyone. This is our group project, the secure streaming platform. This is a end-to-end encrypted video chat. So the goal was to build a simple working example of an encrypted video and chat. We wanted something that clearly shows how encrypted apps work behind the scenes without adding unnecessary complexity. We split the system so the backend handles keys and the browser handles all the encryption aspects. And by the way, I am Ty Larson. I have my team members, Javier Vargas and Brittany Krutchik. So as far as our project overview, right, our main goal was to show a simple working example of a secure streaming concept where the backend handles key storage and the server side uh, does decryption and relay, and the clients handle the encryption. So the system has two main parts. The React front end generates the session key and does all encryption and decryption in the browser. The Spring Boot backend stores the key briefly and returns it to the host and the viewer when they join the session. After both clients have the key, all video and chat traffic is encrypted before it leaves the browser. So for the system architecture, this is a big one. This shows how the work is divided. The front end is responsible for creating or retrieving the AES session key, encrypting each outgoing frame or message, and decrypting whatever comes in. So the backend only stores the session key by the session ID. It does not see plaintext video or plaintext chat. Every part of the system is kept simple, so the encryption story is easy to follow in that sense. As far as the way we handle the encryption, being AES 256 ECB. So then we're going to get into some of these UMLs diagrams we made. First one could be the high-level architecture and the flow behind this. So it works a little bit like this. As you can see, it's illustrated there, but I'll explain and kind of walk through it. The flow works where the host creates a session, the browser generates an AES key and registers that key with the backend. The viewer enters the session ID, and the backend gives them the same key. Both sides then open a WebSocket to the backend. From that point forward, everything sent to that WebSocket is encrypted with the shared AES key. Moving on to the browser decryption workflow, as far as we have another UML here to kind of illustrate that and highlight what we're doing. So this is what happens on the viewer side when an encrypted frame arrives. The WebSocket delivers the ciphertext, the frame parser extracts what the browser needs, and hands it to the decrypt function. From there, the encryption mode we are using is, as I stated before, AES-56 in that ECB mode, so decryption is straightforward. The browser converts the base64 ciphertext back into bytes, applies AES with the shared key, and then from there we get the raw frame or the chat message, where then our graphic user interface, the UI that we made, displays it from there in our working web application that we can show later. From here, I'll actually be passing it over to my group partner, Brittany, to discuss symmetric encryption.
Hello, my name is Brittany Krutchik. My slide is why symmetric encryption for streaming. Streaming sends a constant flow of data and needs low delay. The encryption and decryption has to keep up in real time. The solution for that is AES 256 ECB was used for implementation speed and compatibility. Symmetric encryption is used still for performance. Our project does not have an asymmetric role at the moment. Instead, the backend gives out the session key and the clients handle all encryption and decryption. The key exchange diagram shows key generation, key registration, server storage, and then key use. The first step in that is the host browser generates a unique 256-bit AES key using the Web Crypto API. The second step is the host registers the key by sending a post request to the Java backend. This key transmission happens over HTTP. The third step is the Java backend stores the key in the session key registry in memory. The fourth step is the viewers retrieve the key via a separate API endpoint. The key is then used for client-side encryption and server-side decryption. The dynamic key management is keys are regenerated when a user joins or leaves the session. There are two security limitations. The first one is key transmission. The key is transmitted over HTTP, exposing the session key to MITM attacks. The cipher mode is the use of AES ECB mode does not provide authenticated encryption. The secure messaging security is public chat security, implemented using a basic WebSocket channel. Data flow. The chat allows real-time message synchronization between streamers and viewers. The security is messages are encrypted during transit only by the WebSocket protocol. For secure media streaming, implementation is achieved using React's web crypto to encrypt frames in WebSocket for encrypted frame transmission. The encryption process is AES ECB transform is applied to frames. The access control is data is decrypted on the Java backend before being streamed to the viewers as MJPEG. This is the threat model and mitigations. The first threat is eavesdropper. The strategy is TLS HTTPS for key exchange and switch to AES GCM. For man in the middle MITM, the strategy is X25519 ECDH to verify peers and establish the key securely. For reply attacks, the strategy is to switch to AES GCM. For compromised server, the strategy is true end-to-end encryption to remove the server's decryption capability. Now I'm going to pass it on to our third member of the group.
Hello, my name is Javier Vargas, and this is Demo Workflow. The demo would go something along like this. The host creates a session, gets the session ID, and the stream starts. The viewer types in the session ID and is given the same key. Once both sides have the key, the viewer can see the streamer stream. All video and chat travel is encrypted over the WebSocket. Only the client with the key can make sense of any of the data. We looked at the performance to make sure encryption did not show anything down. AES runs fast in the browser, so our frame rate stayed smooth. The backend was extremely responsive because it almost did nothing besides store and return keys. When we inspected the network traffic, everything looked like unreadable ciphertext, which is exactly what we wanted. Our current limitations. This is not a production system. It supports very few viewers at a time. The key distribution is simple and does not use password authentication. We used AES in an ECB mode, which is not ideal for a real-world encrypted video. We also used raw WebSockets instead of WebRTC. But our purpose was clarity and not building a full-scale streaming platform. If we continued building this, we would add multiple viewer support, a better session security, stronger key exchange methods, and possibly move to something like AES GCM or a full web RTC pipeline. We could also allow encrypted recordings and a nicer front-end interface. In the end, we built a working end-to-end encryption system. The backend provides the key, and the clients handle all the encryption. No plain text ever reaches the server. Even though it's a small project, it demonstrates the exact structure that a real-world encryption apps rely on. Our focus was on making the encryption flow easy to understand, and we feel we achieved that. And with that being said, this is the end of our presentation. Thank you, and we will be moving on to the demo video.
Hello everyone, this is a setup tutorial on the secure streaming demonstration. So first things first is getting onto this GitHub page and then getting this code. Finding a directory within your computer that you want to download these files, opening a PowerShell terminal, cloning the repository, and then from from there, just go ahead and quickly CD into the new folder, which is Secure Streaming. From here, just look for the, there it is, Quick Demo. It is one command. Press enter. A new window will pop up. First terminal is running the backend, and the new terminal is running the front end. Give it a few seconds to initiate. And there we go. So, for example, let's have a Bob streamer. Turns on the camera. Hello. And we'll have a Alex streamer. No, Alex viewer, who will be watching Bob. And once he inputs the name, then he will join his stream and he can say, hello, Bob. And hi, Alex. And seems like there's communication. Only thing that you need to do now is Control C to end both programs, and the demo is concluded. Thank you for your time.